There is one more problem that I would hoped we would have time to do together on Friday in class, but we ran out of time. That's of the kind that I might put on a test for you, and that I'll put a homework assignment up about fairly soon. But it relates a little bit to this problem that we looked at with the sodium line. We said if we line up sodium atoms and treat them as particles in a box and make one long box, what will the height difference, what will the energy difference be between the valence band and the conduction band for those, for that string of atoms? And we got a very, very small number, and we saw that it was very, very easy for sodium to conduct electricity. And we had a little bit of a discussion about how that would be different for calcium and some other atoms. And we want to take a look at a more general case of thinking about conduction in this way, and look at silicon versus diamond. Silicon's band gap is about a little bit more than 1 electron volt. And we could convert that to joules by multiplying by 1.602 times 10 to minus 19. For diamond, it's about 5 times that much, 4.5, 5 times that much. And so what we want to talk about is at what temperature it would be warm enough that the conduction band gets populated with enough electrons to make this conductive. And there's just some experimental evidence to suggest that a ratio of 5.5 times 10 to minus 7 is good enough that we can conduct electricity with any substance whose conduction band is that populated. And so what we have here, this equation that I'm showing, is the Boltzmann distribution. The G's stand for degeneracies, the number of different ways that a electron can have that same energy, the number of different orbitals of the same energy, to put it in words that we normally use. And so we can use this setup to figure out at what temperature silicon with this band gap and diamond with this band gap would become conductive. All right, and so for silicon, we just want to figure out what we have to do to get this ratio up to 5.5 times 10 to the minus 7. And like I said, we're going to assume that the G's are equal to each other. And if we do that, then, and what I mean by assume that is just assume that one level is just as degenerate as the other, and it's close enough. And we get 5.5 times 10 to minus 7 equals this exponential that comes from Boltzmann's work, where K is just the Boltzmann constant. It works out to what we know as R over Avogadro's number, and T is temperature in Kelvins, delta E is band gap. And so we put in we take natural log of both sides, and that drops us out of the exponential. And then we can rearrange and solve for T. And delta E, we said for silicon, is 1.12 electron volts. Here, we use the conversion factor. I would give you this on a test to convert to joules. We do that because the units on Boltzmann's constant is joules per Kelvin. And notice that that per Kelvin is in the denominator, and it's the only unit that doesn't cancel, since this was a fractional unit in the natural log. So we get 900 degrees Kelvin, 900 kelvins, as the temperature at which silicon starts to conduct electricity in a similar way to the way that sodium and other metals do. So that's a bit warmer than we like. But if we do the same math for diamond, it works out to exactly the same setup. I'll just remind you what Boltzmann constant is, R over Avogadro's number, and I'll give it to you on a test if you need it. But if we do the same math for diamond, all of these numbers are exactly the same in this whole fractional setup, except that we put 5.5 here because diamond has a band gap of 5.5 electron volts. And so we end up with 4,400 Kelvin as the conducting temperature for diamond, coincidentally, 4,300 Kelvin is the melting point of diamond. So diamond will not begin to act as though it were a conductor until we melt it down. And so, like I said, this is just one more example that I wanted to work before I put the last homework assignment up. I may make this homework assignment due after the test, but it will be in your best interest to practice it before, even if you don't quite get it all the way right by then.